Hello everyone, welcome to this session. In this session, we will continue to talk about the key concepts in optimization and more kinds of optimization problems. As we have seen in the last session, optimization problem, we want to find the best plan or best design. So previously for the TSP and QAP, we are trying to find the best plan, right? So now let's see another optimization problem. We are trying to find the best plan. So now you have a bag, and this bag, the maximum weight is 15 kilograms. And you have several objects, right? So you can take them to come into the bag. So each one have a weight and have a value. Now we want to maximize the value, but the weight can't exceed the 15 kilogram. So we can see it's like this. The question is which boxes should be chosen to maximize the amount of money, but we have to keep the overall weight of the bag to be under or equal to 15 kilogram. This problem, we call it a knapsack problem. This is also a famous problem and have many applications. So for example, if in the future you are a microelectronic engineer and you work in a foundry, right? So you will often meet the problem about product planning problem in foundries. So you can suggest the foundry about the best plan for the product planning, production planning, right? So a question is that what is the difference between the TSP and QAP compared to the knapsack problem? So first of all, how to represent a solution. So in TSP and QAP, both of them, we can use a permutation, right? Permutation to represent it. But in the knapsack problem, can we still use a permutation? Clearly, we are also optimization a plan, right? We want to find the best plan, right? About which one to pick. But can this one be used as a permutation to represent it or not? If not, what is the best way? So one hint, right? So if you use 1 to say I will pick this, 0 say I will not pick this. This form a solution. So after this session, you can go through this and you can find it from the internet to see if how to represent the best candidate solution of this problem. So all of the above, we are talking about the combinatorial optimization problem. We are optimizing a plan, right? We want to find the best plan. And another kind of problems is continuous optimization, not combinatorial, continuous. So for example, here is a function. So this one we call it the Rosenbrock function. So this is a objective function is here, right? So this one is a search space, and these are the decision variables. So for this function, this is also a mathematical benchmark problem for optimization. In the MATLAB part, you have seen the Ross region one, right? This is another one. So for this benchmark problem, the minimum is x1 and x2. Both of them are 1. And the minimum function value is 0. So we can see this is a contour of the function. We can see the optimum is here. So continuous optimization problem, we are not optimizing a plan. We are optimizing a design if considering engineering. We are often optimizing a design. And let's see a real-world example. This one is an antenna. So we can see this one box is an antenna. We call it a dielectric resonator antenna. This is the operating band, so 5.28 to 5.78 gigahertz. So if you are an antenna engineer in the future, you will always encounter this problem, how to design it. So to design it, we need to find the optimal value of the like AX, AY, W5, WS, so these kinds of things, right? So for each kind of design parameters, we have a different response. So for example, we are interested in the S11 response. So this is curve with respect to frequency, but often we are interested in the worst performance in this operating band, in this one. So the maximum value in this operating band of the S11, the magnitude of it is often the optimization goal, right? So now let's see the optimization problem. So we want to find the optimal design variables of these ones. You can see each one we have a lower bound and we have an upper bound, right? So we want to find the optimal value from it. We want to minimize the maximum S11 with a magnitude in the operating band. So normally when we want to get this value, we have to do simulation. So in MATLAB, there are many toolboxes helping you to do simulations. So this kind of problem, we call them simulation-based optimization. Right. Okay, so that's all for this session. Thank you very much. Bye-bye.